In this lecture, we'll learn about how the energy is stored in a magnetic field. Not only that, we'll also see how much of energy is stored in a magnetic field. Well, to make this calculation, we have to understand a bit about something called self-inductance. Well, you remember the famous experiment? The famous experiment says if you have a particular wire and if you bring a north pole, okay, towards this wire, then a current will be generated because this north pole of the bar magnet will have flux passing through this wire, and we know that if there is a rate of change of magnetic flux through a wire, then there is an electric field or there is an EMF induced, and the EMF induced will be in this direction. Agreed? So there is an EMF induced, and as a result of which there is a current flowing. So we learn an interesting thing, that the EMF that is produced here, so EMF is nothing but, remember, it's a type of potential. So we see that a rate of change of magnetic flux linked through the wire. See, if you keep the magnet here, still nothing is going to happen, no current will flow. You need to make the magnet move near the wire or away from the wire to make a current flow. So you always need a changing magnetic flux to create a particular potential in the wire. Okay, so this is the famous Faraday's law. The minus sign indicates that the current will be in a direction so as to oppose any change. For example, if the north pole is trying to come near the wire, then the current will flow in that direction such that to create a north pole here, and this north pole that has been created due to the wire will repel this north pole, or it will try to make this north pole come to a stop. So it somehow opposes the change. Now if you take the north pole away, so consider in another experiment you have a circular wire, and now what you do is you have a bar magnet with the north pole and south pole, and if you take the north pole away, then the current will flow in such a direction that it will create a south pole. Okay, so the current flows in the clockwise direction, and this south pole will try to attract the north pole, and it will not allow the going away magnet, so it will not allow the magnet to go away. So in this way, the current that is generated opposes the change, which is represented by this minus sign. Now an interesting thing, what amount of current that will be generated in the wire will depend on the amount of flux you are changing, that how much flux you are bringing near the wire. So I can write this phi b as equals to, so when you convert an direct proportionality to an equals to, you always have a constant with I. Now what is this constant? This constant depends on the wire. So this constant says something about the wire. So this constant says that this is a wire with self inductance L will produce an electric current I if the magnetic flux phi is linked with it. Now if a wire has a large value of L, so consider for a wire whose value of L is large, then what will happen? Then for a small amount of magnetic flux, the current produced will be large, because if you have a large value of L, then what will happen is, for a particular current, to generate a particular current, the amount of flux that will be required will be huge. The amount of flux that will be required is huge. Now if a wire has small self inductance, then to create a particular current in the wire, the amount of magnetic flux linking can be small. Agreed. So L carries the information of the wire's property. So how the wire will behave to a particular flux. So this equation now becomes, so as I said, if you have a changing flux near a wire, then a potential will be developed, and that potential will depend on the rate of change of flux. Now we know that the rate of change of flux, the flux itself is a function of self inductance multiplied by current. So what is the final equation? You get minus L di by dt. So what does this equation says? This equation says that the amount of EMF that will be generated in the wire is proportional to the rate of change of current in the wire. Agreed? Now this has some interesting consequences. You have to understand that this new equation. So what is the new equation? Look at this equation. You have d phi by dt. So a changing magnetic flux, okay, is equals to minus L di by dt. So this equation in turn says that if you have a wire, say this is a wire, and if through this wire a changing current is flowing, so what is the current's nature? The nature of the current is it is changing with time. Then this changing current will in turn produce a changing flux. So the flux linked with this wire is going to change, and how the flux will change? The flux will change as d phi b by dt. So this is the nature of the wire. So an interesting thing happens when you say that if you pass a changing current through a wire, a changing flux is generated. So an interesting thing happened. So consider you have a wire, agreed, and through this wire what you do is you pass a changing current. Either the current is increasing or decreasing with time. So when you pass a changing current, the result is the magnetic flux linked with the coil will also start changing, and this magnetic flux will in turn create an EMF, and this changing magnetic flux through this wire will in turn create an EMF that will oppose this increasing current. So this is how the entire thing works out. Agreed? So let me summarize what we have studied till now. So summary 1 is, if you have a circular wire and if the magnetic flux passes through this wire changes, then in that circular wire there will be an EMF produced, and as a result of which a current will flow in the circular wire. On the other hand, if you have a circular wire, if you already have a circular wire, and if a current, when a current I flows in the circular wire, then the magnetic flux linked is phi. You know that the circular wire will produce a magnetic field, and if I multiply that magnetic field with this area, then there is a magnetic flux linked with this current carrying wire. Now if this current changes, then this, so if I change this current, so if I make di by dt, so if I make this current change, then what will happen? The flux linked through this wire is gonna change with time, and both are directly proportional. So the more the change in current, the more will be the change in flux. Now if this wire is not one wire but it is a circle of wires, then what will happen is that this change in magnetic flux due to the changing current will produce an EMF, okay, and that EMF will oppose this increasing current. So the direction of the EMF will be opposite to the direction of flow of current. Agreed? Now, hence, so what is the magnitude of this EMF produced to oppose the changing current? This EMF is actually directly proportional to the changing current, that is di by dt. As a result of which, I can say different wire will have different EMF produced for the same changing current. Again, different wires will have different EMF produced for the same changing current. So the property of the wire is important. So the property of the wire is incorporated in terms of a constant L di by dt. Agreed? So this is the entire story. So we have two story going through. One story is that if you have a changing flux and EMF is induced, and another story is that if you have a changing electric current through a wire, then there is a changing magnetic flux, and this magnetic flux will create an EMF, and this EMF is directly proportional to the changing current, and the constant that tells what amount of EMF will be produced for a particular changing current is the self inductance L, and the self inductance L must carry the information about the wire. So what information the L contains? It contains the information about the geometry of the wire, it contains the information of number of turns in the wire, it also contains the information of nature of the material of the wire. Agreed? So let us not deviate from our main idea. Our main idea was to calculate the energy stored in a magnetic field. So we are going to use these ideas that we have developed to calculate this. So the story says, so let us make the story again. So if you have a circular wire, this is called a solenoid. Agreed? So now we are calculating what will be the energy stored in a magnetic field. If you pass a changing current through this wire, say the current changes as di by dt, then this changing current will produce a changing magnetic flux through this coil, and this in turn will produce an EMF that will try to oppose the increasing current. Now for the battery, now for the battery to maintain a constant current in the circuit, it has to do some work. Agreed? So in order to keep the, so what is the use of a battery? See, battery keeps a constant current in the circuit, but the problem is when you switch on the battery, just when you switch on the battery, the current will increase till it reaches this constant value I, and during this increasing current an EMF will be generated during the increasing current that will oppose the increasing current. Now in order to, we know that whenever you attach a battery to a certain wire, what does the battery do? The battery maintains a constant current, but the problem is when the battery starts giving current in the circuit, due to the presence of this type of wire called as the inductor, there is a slowdown in the process of the current in the wire. That slowdown in the process is caused by this EMF. Agreed? Now in order to work against this EMF, the battery need to do some work, and that work will be stored as the magnetic field inside the inductor. This is the entire story. So the battery is trying to produce a constant current in the circuit. Now to produce the constant current in the circuit, the battery has to work against this EMF. Agreed? Now can you tell me what power the battery must supply to the circuit to keep the current same? The power that the battery must supply should be equivalent to this potential P into I. This is the power that the battery need to supply. Agreed? Now, so what is E? Now E is my L, I. Okay. di by dt. So E is my L di by dt, and I have kept the I here. So what is power? Remember, you can find work done. So what is the total work done? So when I'm saying total work done, so consider the work done in this manner. So consider the wire took a time from 0 to t to maintain the constant current I. So this can be equivalently written as, if I write power in terms of Li di by dt into dt, then what should my limit? Then I should say that the amount of work done in generating a current, I mean in establishing a current I starting from 0, this is the work done that the battery has to do. And this, after a small integration, will come out to be half L I square. So this is the work done, but we have still not reached our destination. Two more things that is needed to be said. This type of system is called a solenoid, and for a solenoid, the value of inductance L is given by mu naught n square Al. Mu naught n square Al. So what is n? N is the number of turns. What is A? Area of the cross section of this wire. So this is A. What is L? L is the length of this inductor coil. This is L. Now putting the value in the work done, so what do I get? I get half. So put this value here, that is mu naught n square Al, and there is an I square. Now remember that for a solenoid, the magnetic field generated inside the solenoid is equals to mu naught n I. So if the I current has been established in the solenoid, then the magnetic field that is established in the solenoid or inductor is B. So from here we can do what? Take out mu 0 and I and keep it separate. So if I take out half, and if I keep mu 0 n and I separate, then I'm left with what? I'm left with n, and I'm left with A with an L and an I. So what is this? So this will be half. The first term is my magnetic field B. Again, in this term, you see, if you just multiply mu naught in the up and the down, so if there is a mu naught in the up and if there is a mu naught in the down, you see that again the mu naught and I will remain, and Al can be left here, and again you get B. Again you get B. So this becomes what? This becomes half B square by mu naught into Al. Now can you tell me what Al is? Al is the total volume of the inductor coil, because A is this area and L is the length. Then what will happen when you multiply area into length? You will get total volume. Then what is the energy stored? The work done is stored as an energy. So you see that the total energy per unit volume. So this is the total volume. So if you divide this by total volume, then the energy stored per unit volume in the magnetic field is half B square mu. So what is the energy stored in a magnetic field per unit volume? So energy stored in a magnetic field per unit volume is half B square by mu naught. This is the magnetic energy stored per unit volume. I hope you understood. So this is done. So let us end our lecture here, and in the next lecture we'll look at Maxwell equations.